Let's look at how to solve optimization problems, which are presented as worded problems. So a rectangular pool is fenced off on all four sides using 100 meters of fencing. So if we label this as X and this dimension as Y, then the perimeter of fencing is written as follows. And we've simplified this problem, so we're not considering the offset of the fencing from the pool. Now what we're looking for is the maximum area of the pool that can be fenced off. So the maximum and minimum of a function can have different meanings in different contexts. So the area is equal to x by y. So what we'll do is solve for y and then substitute that into the area. To get the area as a function of one variable, because we need to differentiate it and set it to 0 to obtain a maximum area. So that gives x is equal to 25 meters. And if you substitute for y, you'll also get 25 meters. So the maximum area is basically that of a square. So therefore the area is 625 meters squared. Now to verify that this is a maximum, we take the second derivative. So because the second derivative is negative, then our result is indeed a maximum, which you can observe from this inverted parabola. A builder has 40 meters of fencing to fence off 3 sides of a house. And what is the maximum area of the land that can be fenced off? So if we denote the horizontal dimension as x and the 2 vertical dimensions as y, then the perimeter is x plus 2y, and that's equal to the amount of fencing we have. So 40 meters. And because we're asked for the maximum area, well, the area is x by y, and we can substitute for x, so we can write this as 40 minus 2y by y. So we can have the area as a function of one variable, and then we can differentiate the area with respect to y. So that's equal to 40 minus 4y. And then setting this derivative to 0, we get y is equal to 10 meters. And substituting for y, we can get x is equal to 20 meters. So therefore the maximum area of the land that can be fenced off is 20 by 10 or 200 meters squared. Let's find the closest point on this line to a point 0, 1. Well, if we choose an arbitrary point on the line, x, y, well, the squared distance from this point to this point over here, we can obtain using Pythagoras. So that would be d squared is equal to x squared plus y minus 1 squared. And now we can substitute for y, so we can write this as x squared plus 3x plus 5 minus 1, so that would be 3x plus 4 squared. And then we differentiate with respect to x. Okay, so we differentiate the squared distance, and what we get is 2x plus 6 by 3x plus 4, which is equal to 20x plus 24. And now we can set this derivative to 0, and therefore x is equal to minus 24 on 20, or minus 6 on 5. And then if you substitute for x into this equation, well, you're going to get your y value, which is 7 on 5. And as you can imagine, the closest point on the line, if you draw the x and y axes to scale, is going to be on the line that's perpendicular to that point. Let's find the closest point on this curve to the point 40. Well, the squared distance between some point on this line to this point over here, we can obtain by Pythagoras. So that will be x minus 4 squared plus y squared. And we can substitute for y to get this as a function of one variable. So we get x minus 4 squared plus 2 root x squared, which is plus 4x. And now we can differentiate this with respect to x. So that would be 2 by x minus 4 plus 4, or 2x minus 8 plus 4, which is minus 4. And therefore setting this derivative to 0, we get x is equal to 2. And then substituting for x equals 2, we get y is 2 root 2. So the closest point is somewhere here on that curve. A projectile is launched to a horizontal distance r, and we're asked to find the angle theta that maximizes the range r. So we have the initial speed, we have the launch angle from the horizontal. So if we differentiate the range with respect to theta, we get 2 v naught x squared, which is a horizontal component of the velocity, on g by cosine 2 theta. And if we set this derivative to 0, so for this expression to be 0, 0 is equal to cosine 2 theta, and 2 theta must therefore be a multiple of pi on 2. So because the launch angle must be less than 90 degrees, then 2 theta must be equal to pi on 2, and therefore theta is equal to pi on 4. So the angle that's going to maximize the range is 45 degrees. A rectangular prism has a volume of 24 meters cubed, and we're asked to find the dimensions of the prism that will minimize its surface area, assuming it has a square base. So therefore the dimensions of the base are the same, and it has some height y. So the volume is therefore x squared y. And the surface area is 2 times the area of one base plus 4 times the area of one side. And now we can substitute for y to make the area a function of one variable. So we have 4x multiplied by 24 on x squared. And that gives 2x squared plus 96 on x. And then differentiating the area with respect to x, we get 4x minus 96 on x squared. And now you can set the derivative to 0, and that's going to give you x is equal to 2.9 meters. And if you substitute for x in this equation, that's also going to give you y is equal to x. A rectangular football field is to fit into an ellipse with radii 50 and 30 meters. And we're asked to find the maximum possible area of the football field. So if we take x and y on the ellipse, then the area of this rectangle is equal to 2x multiplied by 2y. And from the equation of an ellipse, so that's x squared on 50 squared plus y squared on 30 squared equals 1. Well, you can substitute for y to get the area in terms of x, and take the derivative of a with respect to x, and set it to 0. And then that's going to give you your x value, which you can substitute into this equation to get the y value, and finally substitute in this equation to get the area. So leave your answer in the comments.